All right, I guess we're live. Hello, everyone. Um, if you can, if you can hear my voice, can you please leave it in chat so I know that the audio is okay? Hello, can you guys hear me? Um, Hopefully you can. And I suppose that you guys do. Um, so welcome for the people who just joined in or this is like their first time attending this stream. We are trying to make a simple programming language that's called Comet. Um, it's a little match between Go and JavaScript. Um, and we're trying to make an interpreter for it. I guess the last time I had the code for last time in a feature branch that's called a parser, and we finished the last time by creating the applet parser for math expressions, and those are the foundation of our parsing algorithm, and we will be using whatever we started making last time to make the rest of this request. So today I'm planning to do a little bit more refactoring on the testing side. Because if we saw like before, we pushed a feature branch that didn't have anything around testing. So we had these dummy tests um, that kind of bootstraps the parser with some given math expression and parses the root node. And this, we assert that the root node is not null, but we don't know what's the generated value of the root node. And actually now we want to have assertions on the root node itself. We finished last episode by implementing a really cool feature, which is the node visitor type, which will allow us to perform additional behavior and checks without actually modifying the AST after creating it. This is good because we can use this pattern to kind of implement easier testing for our parser. Okay, if you have any questions at any point in time, or if you see if you spot some kind of bug, please leave it in chat. And with that, I guess I'll just jump in. So yeah, so the main idea that we have is we had a parser, and the parser generates a root node. And we want to make sure that the actual generated node is of some kind of structure and in some type of sequencing. So we want to have for this type, we don't want to make sure that the plus node here is a binary expression and it has as left param 1 and its left param 2. And same thing for the multiplication here and for the subtraction here. And to do this nicely, we would make use of the visitor pattern that we implemented last time. All right. So yeah. So the end result is we want to create this parser with this root node, and the root node should accept some kind of testing visitor. Visitor is gonna be like a testing visitor for now. And the testing visitor, we wanted to implement the visitor API. Not that. Node visitor API. And we want this to be applicable on everything, actually. So I want to implement some logic here so that we visit in some kind of sequence these types of operations. And after accepting the testing visitor will make these kind of assumptions. So we will traverse the AST in a given order, and we will test by order of traversal. So this is so I have an idea in mind, which is like to implement this. Let me draw it out for you. I'm sketching a lot. So the idea here is, So the idea here is to implement something. Let's suppose we have this expression, and the expression is a equals 1 plus 2 multiplied by 3 minus 4, just as the expression that we had before. And we know that the parser should at least generate this kind of parse tree. Should generate 1, and then here we have a node that has plus, and then that has a multiplication node that has here 2, and then that has here 3, and let's see. Yeah, this should be here, and I guess it should have minus 4 somewhere. So we should have like another additional minus node. Yeah, I probably missed the minus here. Someplace. All right, let's not care about it. It will come anyway. It will come eventually. Actually, let's try to print it. Okay, so this is quite similar that we have to what do we have right now. So yeah, so the minus expression would be like the top level in this case. So we'll have something like this, minus and 4 here. And this parse tree, we want to make sure that actually we are visiting in this order. So our testing visitor we wanted to visit like the tree in this order, which is a pre-order post-order traversal. Actually, it's like an in-order / post-order traversal. But the terminology itself doesn't matter. We start from here, and then we visit like the deepest node in here, and then we will reach some kind of terminal expression here that has no children, and we want to make sure that this is actually a token and this is a 1. And when going up, we want to make sure that this is actually a plus operator. And then going left again, we want to make sure that this is a 2 and this is a multiplication operator. This is actually a 3 and this is actually a 4 and this is a minus operator. So we want to make assertions while traversing the tree, and not actually generating the boss tree and then doing the assertions later. So we can implement this by implementing this, by implementing this testing visitor, and the testing visitor itself should take some kind of nodes or statements or expressions. So let's have a node. We'll have a bunch of nodes, or at least the expected nodes that we will need to test about. And we will need the current pointer, which is just an integer, to know what index are we actually matching in here. And I guess this is it for the moment, but probably we'll need something else. So what we need to do is like expression. Whenever we visit some kind of expression, we should like skip it, I guess. We should never actually hit here, so we should like keep this easier. So a root node will do statements that for. So for each one of the statements, we want the visitor to accept the current key. And we don't really, and actually we are not testing the actual statements. Statements, or at least statements. And for a binary expression, it would be something of expression dot left dot accept t, and we do the same for the right. And here we should assert on the type. We'll do this in a second. A prefix expression, we don't have any prefix expressions yet, so I'll leave it open. And here we should we know that the expression itself doesn't have anything else, so we should do something such as expression dot the actual value. So we want that the t dot expected of this value, so like current node. And we should cast the current node to a number literal expression. And we should assert dot true of t dot t. That's okay. And this we need like a t, which is in this testing.t. And we want to make sure that this is actually happening, that the cast is possible. So this is actually the expected type, and we will need to make sure that the assert dot equal t dot t, that the current number literal, that the expected, which is the current node, dot current number literal, dot the actual value, which is an n64, is equivalent to the expression dot actual value, which is the n64. And if this works, we need to increment the next one. We should increment the pointer. And this is like a little testing helper for this. And we want to do the same for both, for this and for the binary expression. Right. So, but only this time we will need a binary expression. And we want to make sure that the current binary expression, that operator, we know that there is an operator dot type, I guess, or token, at least literal. We want the literal to be the same for both of them. And again, we do the same and we increment. And the test is like necessary to happen like between both of them. Yeah. So this is for the number literal, for the single number expression. So now we need to fill in the expected by some kind of node. And we give it like the minimal number of stuff that it needs. So it needs it needs t, but it needs also the nodes. So we know like the first one is a number literal expression with the actual value of 1, or at least of n64 of 1. And we know the second. Okay, so we have 4 of these. So one is 1, one is 2, 3 and 4. and between them we have binary expressions. And the first one is the binary expression, and we only need to fill in the operator or the necessary part for it to work. So the operator itself needs a token, which will need the literal, and the literal in this case is a plus, I guess. Maybe the literal. Yep. And we will do the same here. So we have 2, and then we have some multiplication operation, and then we'll do the same here for the minus operator, right? Trying to do this. So if we run the test now, it works. And if we make here, so let's try to see if this actually kind of breaks, if this is not what we expect. So yeah, this breaks because we expected to have a multiplication next, but we didn't have any, which kind of justifies that our parse tree actually works, right? Alright, so now let's start to refactor this a bit before actually moving on. So we need like some kind of testing functions. So we know we can see like this operation kind of happens a little bit of multiple times. So we can refactor this into some kind of method. So let's do it st this in visitor, and then let's see a search node. So this should take in. So okay, so let me move this code in here and see what it will need. So it will need some kind of expression. Yeah, so we can't actually do this, I guess. So this can be refactored quite easily with Go, I guess. I guess we should have like a function, an assertion function per given expression. So let's lumber literal expression. So if we do this for now, we need to test the actual value. Or at least I should copy this instead. And this is the assert number literal node. We will need to have something similar for the assert binary expression. And we should paste in the code that we had before, and yeah. So now I guess extracting this is okay, I guess. Now we can call in t.assert binary expression, and here assert number literal node. It would have been way cooler if we could have extracted only the type. And then mapped each. I don't know if we can do like, yeah, we can. I guess we can do this. We can extract mapping functions by type, and then we reduce the added complexity. So we can have a declaration of mapping functions. So let's define like some kind of type, which is a function go with a destin function, node assert function, which is a func that takes in some kind of node, and then it takes some type, which is a reflect type, and does something with it. We don't know actually what it does it right now, and we will need to have some kind of map bounded to it. I'm not sure if we should like bound this to a to the testing visitor, or actually leave it. Let's try it this way. So let's have a assertion function, which is a map of type so I guess doing this doesn't really matter. And we should only take in a node assertion function. I don't know, probably we'll need the type later or not. And then when actually creating this, so we should create a function that will return this on new testing visitor, which will take in the testility, and it will take some nodes expected nodes, and this will return a destin visitor. And for now, we should create a visitor here, which is a destin visitor of whatever we had before. We have the expected, and we have D. All right. And now we should like initialize the visitor dot assert funcs as a make of some map of reflect dot type and an auto assert function. And now we will like set some functions in here. So we'll go like the visitor of assert functions of reflect dot type of is it a, can we like assign types? If I do like type equals, not sure if this actually can be done. Can we have node as the type? I highly much doubt it. Yeah, the actual types are not expressions, but I'm not sure. Can we do a reflect that type of node? Well, that's a bummer. So types are not first-class citizens, which is weird. So I can't assign types as they are declared or literally into some kind of variable. So we can't write this nicer for now, I guess. Or can we? So I wanted to assert, I want to group. So the idea is to group these functions. I want them to be, the logic itself is just taking an expression and testing the expression or the statement. And the type of the statement itself All right, I guess it's fine for now. So let me do this. Probably it's not a good idea. We have a separate component for this, so just let's make the logic in there for it. And yeah, so we have single number expressions. I would like to make a couple more tests. So I actually like create a tests, which probably struct something, which should contain the expression, which is a string, and should have an expected nodes, I guess. And I guess that's it. And in this case, the expression is I want to have some elements for this, so let's do this. And the expected for this case is this. And now for every test, I want to create a new parser, do this, create testing visitor, and then give it the test.expected and create this from the test.expression. And call the root node.accept on the testing visitor. Yeah. And this should take in T as the current assertion context. Right. And if we run our tests, this should still pass. Oops. Something went wrong. Alright, the test still pass. So let's add another count of tests. So the expression would be 1, and the expected should be a node of a number, a literal expression that has the actual value set to 1. Trying to run this again. It works. One binary expression, one other binary expression. That actually, I I want to have this like for all type of operations before actually mixing them up to guarantee that we support every binary operation. I'll need this, and I will need something like minus. Actually, it was a bad idea to actually copy them. So we have a number expression of the same number expression. For variance, I guess I will make this 2 or 21 for that matter. And here you have a binary expression that has the operator op as a token with the literal as plus. Now I can copy and paste and paste and paste. Oh, that's no good. I should copy all of this. And paste like for a couple of times. And now let's have over right. And if we try to run this, that's still pass. So that I guess is all for binary expressions. So let's try and do other type of expressions. So here we test parse simple math expressions, and we want to test like a couple of things. We want to parse. We want the ability to kind of parse parenthesized expressions, and in this case we should be able to. Okay, sorry. We should be able to parse this. All right, and we want to be able to parse 1, and the first one is yeah, is a 1, but in this case I don't want a binary expression. I want a parenthesized expression. I don't even know if parenthesized is actually correct in this case. So let me try and like fix this real quick. Let's go to our nodes section. I want to be able to declare my new struct parenthesized expression. A parenthesized expression is any expression that actually has an expression inside that have it as an actual expression, and implement a expression so parenthesized expression will just call the visitor dot visit parenthesized expression with b, which means visit parenthesized expression with a parenthesized expression. All right. Okay, and for the statement and expression, we'll leave them alone. Now constructing this will mean like we need to give it some kind of expression. We can't parse it right now. That's fine, I should implement this later. We know that we have the actual setup here. We want to make sure that our visitors actually work. So we need to implement this function and we move it to somewhere along here, and we are making sure to do like expression dot accept t. So actually it's not the parenthesized expression itself, is not that interesting, but I guess it should be like more interesting to see the structure or the hierarchy. If we try, okay, I remember we had another print in kind of visitor. Yeah, this one we should deal with also. Let's move it down here, and we will just do that print indent p.buffer right string parenthesized expression, and then we'll do like p.accept that, I don't know, we should call visit expression probably. Expression dot expression. Expression. And we should go back to the node and then make this probably public, just for the sake of it, because we will be accessing it from other modules. Yeah, expert. Right. This is fine. Let's go to tests. Okay. So my keyboard is actually arguing with me. So here is expression. And going back to the main, should be expression. All right. So doing this won't do anything, but when actually doing something such as this, it will blow up, I guess. Yep. Blow up because we don't know how to parse this. So let's go back to our parser and try to parse something similar. So when parsing an expression, we call parse internal. And parse internal, if I remember, has a prefix function for every current type. And it will call that prefix function wherever it finds the current type. And we want to have a parent, I guess, which is like the complex or the precedence for a given parenthesized expression, and we should register this kind of prefix operation. So we want p.register prefix function as p.parse parenthesized whenever we find lexer dot open parenthesis, and we want to create this method, and the method should so where do we have all our parsing expressions? So yeah, so since it's like just another binary expression, we should like take in the first part. So we should create the p equals a parenthesized expression. and I guess so the current token is, well, since we're here, so the current token is this, and we have some kind of expression, and then it should end like this. So we should set the expression to p.parse expression, and when we do p.peak, do we have a peak function? Next token dot p.expect maybe? Advanced expect, yes. We have something that's called p.advance and expect to have elixir dot close parenthesis. So we want to advance, but we want to make sure that this actually works. And then we return a parenthesized expression. And if we try to do this, probably we'll end up missing something. Yep, I guess our stack is blown up. Yeah. Because we should probably consume this. So p.advance and expect elixir.open. So how about this? It still blows up. Expected something and got 3. Okay. Let's see the expression. All right. So let's debug. Yeah. So when do we hit this? Which is not actually a line. We hit this exactly when the current token is actually an open in parentheses, and the next token is something else. So we advance, and the current token now is 2. We go into a parse internal expression, we parse internal, we do the same here. If we have something that is 2, we know how to parse it. Now we go back, and then the left is a binary expression that has a plus in it. Okay, it looks okay here. Now this is the parenthesized expression that has an expression, but here it's kind of blown up. It's blown up for some reason. So let's extract this here to make sure that we aren't actually making a mess. Expression. And let's debug here. What happens after getting here? So the expression for now is this, and the current token is 3 for some reason. So the 3 is never consumed. And the next token is a literal. So this should actually parse the next. Yeah, advance and expect is actually weird. This is not what I wanted, actually. I wanted something like this. Expect next. Huh. Yeah, this one will actually take the next token. All right. And we want to here do expect next, probably. And we want to advance to the next token. So at this point, all right, so moving on, P will actually point to the minus section, and it will go back, I guess. Yeah, it panicked in here. Yep. Yeah, it panicked. Yep. Kind of made a little mistake in the print-in visitor. So we need p dot expression, or at least expression dot expression accept p. And if we try to run this, now we see that this is not good. We see that so we have a parenthesized expression that contains, all right, oh come on. So p dot indent plus equals 1, indent with at least. We'll do the same here so that we can get a little bit of an indentation result. Yeah, so the parenthesized expression now is actually containing the binary expression, which is good. Yeah, so let's go back to our parser test now and see how well it will do with this. Right, now it passes because we can actually recognize this, right? So we want to make sure that the priority given, so let me go back to the parser. Yeah, so let me go back to the parser and make sure that this I want to make sure that so what if we do this? We do we want to have something such as 1 multiplied by 2 plus 1. I want to make sure that the other one actually takes the parenthesized expression takes precedence. And here we find that we have 1 on the left and the parenthesized expression on the right. Cool. Now what about doing this? Yeah, so the left is actually 2. And on the right, we have minus with a parenthesized expression. And if we switch this to a plus minus operation, we wouldn't see much of a difference. Okay. How about having a multiplication here? I don't expect to have much of a difference in here. All right. So a plus, and then we have a bunch of numbers. And then we have the post tree. So the post tree is kind of getting generated correctly. There should be like enforced, but I got a bunch of tests. So if we have 1 multiplied by 1 plus 2, so we need to know that this is actually seen, and then this is, and then this is in the order. But we need to find that we actually have seen a parenthesized expression that kind of englobes these two. So we have a parenthesized expression, and then we have 1 and then 2, and then we have a binary operator, which should be in here, I guess. Yeah. So if we run the test, all right, it blows up. So why did you blow it up? Where do you... So I have no idea where it broke. Assert binary expression? Oh, really? Right. So we had a parenthesized expression. I can't seem to find the assertion part of it. Yeah, we just currently accept this. Yeah, no, we want to make sure that the actual from this solver. Nope. It's still panicking. So it's a null pointer dereference. Okay, this is kind of weird. Right. So let's see where did they blow up. Let's debug this test and see which operation caused it. We know which operation actually to cause it to blow up. So this is a parenthesized expression, and then the next time this happens, so the current test is 1, so it doesn't matter. Yeah. So asserting that this is a number literal, and the number literal of the expression, which is actually 1, huh. Okay, so it blows up in here. And this gotten called by, is it number literal? This is called by is it parenthesized expression? So let us remove this, and let's do the same again. So the current test is this. Skip a little bit ahead. Yeah, so let's try and debug this. So this went into the root node, and then we had to accept a bunch of statements. Then we accepted a binary expression. We asserted that the actual expression is a binary expression. Yeah. So it's a binary expression. So we asserted and it blowed up. Yeah, what's the problem here? Oh yeah. So before the expression we had actually 2 operators. Lucky me. Okay, let's try to run it now. Yeah, so invalid memory, trying to dereference something that is not there. All right. Debugging again. Artist is 1, 1, 2, 1 minus 2, 1 minus 2 times 3. Should probably remove this, but it gives a good indication of where am I. So we know that 1 passes actually, and 1 times 2 actually doesn't pass. So let's try to debug this. We go and see every statement. We see a binary expression. And the current expression has a left as the actual value of 1 and the right as the actual value of an operation. Say plus from 1 to right 2. Oh, right. Well, this is not good. Oh, right. This is a parenthesized expression, which is good. Okay. So we visited a binary expression which accepted the left and tested it. And we're asserting that the binary expression is to the left as, all right. So what's the current pointer? The current pointer is 1. And the expected is that the first one should be some kind of operation. All right. So we do this and we say it's okay. We see that this works and we increment and we go back. Then we accept the right and we do this, going back to the parenthesized expression, letting it accept the expression, and it will visit a binary expression. Alright, so when accepting the left part, a parenthesized expression probably should increment the count, I guess. So the problem here is that it can't cast because the t itself is, yeah, I don't know what's that, but the pointer is 2 and the expected into is a parenthesized expression. All right, I guess before actually doing anything, I guess, all right, it's still failing for some reason. Why is it failing? Doesn't have a dereferencing of some kind of null pointer. Not cool. All right, let's break in here. I thought I figured out the bug, but apparently I didn't. Probably should isolate. But for some reason I still think it's worth it. So t now, in this case, is 1, and the expected has a parenthesized expression. And going in here, you'll see that we have a number literal, and we will assert number literal, and the pointer is 1, so you should take, what's the test for this? It should find the parenthesized expression before actually. I'm actually confused why this is like left after. Yeah, now it passes. Well, the problem was here. I thought it was in here. And this is an increment, but we should make sure that the actual value is actually a parenthesized expression. Actually, we don't care. We only are interested if this is actually, if the cast actually passes. And if it passes, we know that the actual position, the actual expression is a parenthesized expression. Yeah. All right. The testing visitor should search on the structure of the tree while doing the traversal. The expected nodes are given in I guess in order traversal. I'm gonna say ish traversal in order traversal order. Change to the structure of the AST should make the testing visitor fail affected not updated tests. Structure and visitor, not visitor, or whatever I wrote. Visitor. Okay. I guess this is about it about math expressions. I guess we should try to do we should stop doing math expressions for now and then go on and do some additional statements. So let's figure statements out. So we know that Comet has some kind of statements, and the only statements that we have are the declaration statements, such as variable declarations and addition, I guess, bigger, equal. What do we have else? Oh yeah, and then return statements. And those are the two that we have. So let's try and make this work. So let's go to the test and let's create another test. And what's the convention that we did here? So we did test parser, parse something. Test parser, parse simple, parse declaration statements. Declaration statements. So we want to test, want to match something of something like this. Var a equals 10. And we'll end up doing the same pattern. But for now, let's keep it short and simple. And let's create a visitor. And the expected are a bunch of nodes that have, So the first one should be a declare node. Actually, we should only have one declare statement. Okay, so let's think, how will a declare statement look like? So in theory, a declare statement should look like this: a variable, which is a var character, a equals an expression. So we would want to have a tree structure that is like a dec statement that will have the var token, the identifier, and the expression. So this is, so when asserting on this, we should probably create the declaration and then make the test nodes, that we should make the declaration statements aware of the expressions inside, because visiting the tree structure will end up like visiting var, then the identifier, but those are a bunch of constants, and here we'll have the expression, and we should like have the expression tree here and assert on this. Yeah. All right. So let's go back to nodes. Let's make something compile at least. Let's have a declaration statement. Type declaration statement. The struct that has, we know it has a var declaration, probably, which is a token. Should we, let's, we know, alright, so it's var token, which is a Lexer token, and I will have the identifier. Which is a Lexer.token itself. We know that both of them are going to be like tokens, and I have the expression. Want to implement a statement, and when visiting, we want the visitor to visit a declaration statement, and with the, I should have like a visit declaration statement with the declaration statement in here, right? And for those, I guess I'll leave them empty for now. We should like make adjustments to our printing visitor. And we will just do a print indent, beat up buffer, that write string, currently, not currently, I'll just do a declaration statement with some given identifier. Statement dot identifier dot literal, and then we should do p.indent plus equals indent width, and recurse on the statement actually. Expression dot accept the statement. the statement, the actual P, I guess. Alright, so this should fix this one. Now we should fix our testing visitor. A node visitor. Alright, so yeah, that's actually not the place for it. And the declaration statement should make sure that the actual node is a declaration statement. So we should do this, right? And declaration statement, and we should like advance the pointer, and then we should like do the statement dot write, and we should make sure that the current node identifier is actually equal to the statement dot identifier dot literal. Yeah. Right, and then when advancing, we should make sure that the statement dot expression that accepts the actual visitor. Now it kind of works up. So if we try and run this, it will blow up because for the time being we can't parse. No parsing function for the given var. So we want to assign some parsing function for the given variable, or, which is better, we should, when parsing the statements, actually pick it up. So we switch on the current token dot type actually. Yeah, I guess I need a case. Declaration var, I guess. I don't remember. What did we call it? I don't know. Did we call it like? I had a keyword which is a var, and we had tokens for this. Where the lexer that go? All right. So the tokens, yeah, we have here. We had it like token lexer.var, right? So it's lexer.var. If we find this, we return p.parse declaration. All right. So let's start with that. So we p.advance expect that the current token type is a var token, and we create the declaration node. Declaration statement, return declaration statement, and we say that this is a declaration statement that will have a, actually let's do this here, and then let's do that the token, the var token is p.current p dot I don't know if we have something that says expect. We only have stuff that are like this. Okay, doesn't matter. So declare advanced expect should match that the current statement is a var. All right. Right. Where from here? Where was I? Yep. And the declaration statement dot identifier should be a and p dot expect next. We want the next to be a nexer dot identifier. Actually, this is expect current, so I'll do the same here. I'll expect to be an identifier. And p dot expression. And declaration statement dot expression equals p dot parse expression. So now the current statement is something else, I guess. So if we run this now, it still blows up for some reason, but no parsing function found for equals. So somehow, so I should parse an assignment operation. We have an identifier and p dot advance and expect that the nexer dot assign, I guess. I should skip the assignment also. And index out of range with 0. Don't remember where did this blow up? Oh yeah. So I'm actually not interested in this as much. I want to see the actual parse tree generated. To know if we have actually something that we can like test. So I have a root node, a declaration statement for a, and then visitor number. And if we say 1 plus 2, we'll have an expression that takes a declaration number. And if we have a, say, I'm interested actually in seeing if this actually will work. And saying var b equals 12, 1, 2, 3. What will happen then is a declaration of a and then declaration of b, which is cool. All right, so I guess our declaration node is actually working. All we have to do is like create it. So we'll have a declaration statement, and the actual token will have a var token, and we are interested in the identifier, which is like a token that has a name. This is a literal, and the literal in this case is a, and it has one expression, and which is a number literal node, which with actual value equal to 64 of 10. That's probably it. Let's try and run this test and hope it doesn't blow up. It does blow up. So the index out of range with length 1. Yeah, it's probably a good idea is to debug this. Yeah. So let's see what happens. So we know that we accept in a root node, and then we go through the statements, and then we go through the statement. You have the visitor, and then in the scope we have the var token. So we try to visit this, and then the expected, the pointer is 0, so we check the first one. The first one is 0, and oh, I see. Yeah, I see the bug. So this should have been like outside in here. So we should have said like we would how about now, how about this? Yeah, the test passes. Just cool. Because we know we will see like this after this and post and pre-order reversal. As is, this never runs successfully from the start. Yeah, they never do. Alright, so let's try with probably an expression. Yeah, let's try with 12 plus 12, or plus 2. So this should blow up. Yep, it does. And we'll do the same here as we did before. Oh, there is another, a nicer way to test this. To actually not have to repeat yourself too much. Binary expression. And the operator is elixir.token. The literal is plus in this case. If this works, we will write similar tests for the other one. Yes. Okay. So. Okay. So let's try and do the same here. Actually, we'll copy the structure from here. Because I know we'll need something similar. And the expected. We have a bunch of stuff. And we have the expression to be something of var a equals 1. And why is he yelling? Oh yeah. And I have the expected to be something of this. Be this. We have a, and I have a number literal of 1. And for the rest of the test, I guess we can copy it from here. Right, so this will make this should work for everything. Okay, now let's add a bunch of more tests. Yeah, so let's add the one that we have like 2 declaration statements. So yeah, 1, we have 12, and then we had a binary expression that I'll copy from here. So this should still work. Now for the fun part of having 2 of them. Var a b equals like a plus 12. So the expression we have number literal expressions, and then we have, oh yeah, we probably should find, yeah, we made a little mistake here by treating this as a token. I'm hesitant actually to treat this as a token because I'll need it here as an expression. So what I want to have is to have what I had before, but to have another declaration here that has this time b, and have a parenthesized expression containing a, which is a identifier expression, name of the identifier is a. And then the binary expression, and then the 12 value. So this is what I was like, what I want to have actually. Which means that this is another node that we will need to traverse. Or not. So let's keep it like this for now. Let's not mix them up. Let's create the identifier expression. Identifier expression. And for a given identifier expression, all we need is actually the name, which is just a simple string. Yeah, the receiver types are wrong. Yeah, so on the visitor would accept, so it should visit identifier expression. Now, again, as always, let's try to fix our printing visitor. And this will just do an this will just print indent, heat up buffer, array string. Identifier expression of something, and this something is the expression dot name, and we don't have to do anything else in this case. For our parser now, the cool thing is we'll do the same. Implements node visitor. All right. And this time we'll need to do something a little bit different. So we should take the current node, so now it's an identifier expression. And we want to do this before actually moving on. So we want the current identifier expression, that name is equivalent to the expression that name. I want that to be equal. All right, so now we can test. And again, no parsing function found for identifier a. Yeah, I guess this won't produce something because when parsing the expressions, yeah, we never told the parser how to parse expressions. So he parsed the number and then he parsed some kind of parenthesized or expression, but he actually never learned how to parse an identifier, p.register prefix func, and then p.parse identifier. Whenever you can find an identifier, if you find an identifier first, just like do it and parse it as an identifier function. And this will just do p.advance expect okay, so this is way far than I wanted. I want something just here. So when I return, so the number value, I want to have an identifier expression, and I want the name to be the current literal. p.advance and expect probably this to be a identifier. Yeah, and this probably will. So we expected this, but we got something like this. All right, so that means that in our parsing function we get something that is not okay. So what's wrong? Let's go back to the parser test and see what's wrong. Should probably break here now and run only this test. Yep. So let's debug. So the first time it's var A, it's var A. Oh, it's panicking. Huh. Interesting. It's panicking on the second one. Alright, so the second one is var A equals. Yep. Oh, the second one is panicking. Alright. Let's debug again. So let's visit the root node. We have a bunch of statements. We are to the declaration statement. And we have the expected, which is pointer of 0. And the expected now is the var token, we have an identifier which is an A. So we are able to guess, and this is equal, and we increment, and then we go to the statement. A binary expression, we have, what's the expression now? It's a plus. So we visit the left, we assert the binary expression. So the current pointer is 2, the expected now for 2 is plus, but the left and right, yeah, it doesn't matter actually. Alright, so this will pass. Assert binary expression, and the right is visitor dot visit literal number literal. Okay, so the expression now is something. This should work. Increment. Go back, go back, go back. Go back, go back. Go back. Okay, so this is actually not failing. Oh, I see. So this is what's failing. So we are actually, so we can't actually parse. The Lexer has var a equals 1 plus 2. So we parse the first statement, we advanced. Now, if we find a var, that's parse declaration, we take this, take that, then we take the assign. Now the current is, alright, so we do parse expression. The parse expression should take internal, and the prefix functions for that we have. Oh, right. So in parse parenthesized, we expected so after parsing the expression of A, it's probably this one is the culprit. Alright, so now our current token is the identifier. So let's jump to parsing the expression. So actually parsing, so parse internal, yeah, so parse expression couldn't parse, so it calls parse internal, and parse internal takes the prefix functions, alright, so what do we have as the prefix functions? We have identifiers. Let's go back. another debugging stream. So we have a parse expression. That should call parse in journal. And has is true. Now calling the prefix, we'll do parse identifier. Now left, is an identifier expression. And the next token is 12. So it's consuming one more than it should be. The parse identifier, so it shouldn't actually consume it. Yep, that was the bug. So we are consuming one more than we actually want to consume. Now it actually works. Alright, let's go back to the parser tests. And we have another parser now that gets in another parsing expression. We have a bunch of statements and we have a parenthesized expression now on them. We are 1 hour 42 minutes in. I guess I can do one more. I guess I'll do like another 20 minutes. So let's add in a return statements to complete statements today at least. I want to actually group our statements. And then let's make the same thing here. And then this is a return statement. We have a return token. And then an expression. Statement, and a visitor should visit return statement. Right, now let's do another one for like here we have a return statement. Actually, we don't need this because and we do this. Actually, statement. Cool. Let's do the same for the testing visitor. The test here. I would like to group them both here in the end. Alright, so how can we test return statements? It's just like all of them. All the statements kind of are been tested the same. This could have been refactored if we could have like treated the types as first class citizens, but apparently we can't, or at least I don't know how to do it. Expression. Right, so this is a current return statement. Current return statement dot expression. Actually, we don't need to test anything in here, so it's irrelevant. All we want to know is like we have a return statement. Same expression dot accept t. Yeah, that's actually true. So I'm gonna copy again this. Parse return statement. And the only test I'll start with is return 1 plus 10. Well, I'll return 1. Alright, and what do I expect is a return statement, an empty one, and a number literal, which is 1. And I won't need most of the other things. Alright, so if I run this, it will blow up. And let's try and make it work. Actually, it's not gonna be that hard. It's more or less the same as per the return statements. So our parse here, we have a parse declaration. Here we have elixir dot return p dot parse return statement. Let's create this. And let's copy this over. Okay, so let's put it in here. So we will create a return statement. Is a return statement, and var token, which is a var token, return token is the current token, and we will make sure that this one is a return, and return statement dot expression equals p dot parse expression. And then we return the declaration statement, or the return statement actually. Okay, so let's try. So we had one test for this. Let's try to run it. So it didn't blow up. So let's actually try to see the parse tree generated. So if we do return 1, so we had a return statement that had visiting 1 number. If we do return something that is an expression, would have a binary expression, would have something such as 1 plus 2, a parenthesized expression, and if I multiply by a, it should have a binary expression that 2 times a. Alright, so the return node is actually working, so let's make some tests for it. So we need a bunch of tests. So one simple expression, some kind of operation. So we have return a number literal, another number literal, and this. Maybe a parenthesized expression. which is a return statement, a1, a parenthesized expression, a2, a minus, a1. Constructor on this. All right, this didn't work. Parse return statement. Okay, so what did we blow up? So we have a parenthesized expression, which is here, and we have a number expression, which is 2, and then minus, and then 1. And the number literal expression is before. Now we needed another binary expression here, which is the plus. Probably this was the issue. Yep, it is. Let's add 1 where we return something other than an integer. So we need a return statement and an identifier expression of something of value. So we return value. And this works. And we return something else, such as some math expression. As a, we should have a binary expression. And parenthesized expression. A binary expression. For which we had the number expression, which is the 1. All right, so this, yeah, here we have a. All right. Now the current state is we have a bunch of tests. We have an easy-ish way to kind of test the parser tree structure, and we actually have the parser now is able to recognize math expressions, parenthesized math expressions, and variable declarations and return statements. I would say that we made like pretty good progress today. We are just about the 2 hours mark. I'm feeling a little bit tired. So yeah, if there aren't any questions, I guess we can call it a day. Next time probably we'll get into more expressions and probably more statements, but the goal is to start handling function declarations and probably a little bit more complex statements such as if statements and for loops. Okay, seems that there are no questions today. Yeah, and today's stream was pretty quiet. Yeah. I guess the code for this will be pushed into the branch. I won't merge it into master unless we finish the parser first. But for now, we'll just leave it at the current branch. I'll push it after the stream ends. All right. See you guys same time next week.